Hello everyone. Today I'm going to give you a presentation about employment of non-polyurethane polymer systems, which is a step for energy efficient coating systems. I will begin with history of polyaspartic coatings, its chemistry and applications, then comparison between polyurethane and polyurea, and which amine to choose for their reactions. Also, I will talk about the advantages of polyaspartics. I will end my presentation with the outcomes of the test we conducted to compare polyurea and polyurethane coatings. Since 1930s, numerous researches have been conducted with the invention of polyurethane. On the other hand, polyurea chemistry was invented in the 1970s. But there was a challenge. Set time for polyurea was too short. Practical application of it was possible with the development of special equipment. In 1992, polyaspartic resin was invented. After 19th, set time was increased to 25 minutes from just 3 seconds. It enabled the commercialization of industrial maintenance polyaspartic coatings in 2000s. We can say that it is a relatively new research field with a great potential for improvement. Isocyanate is a highly reactive molecule due to the nucleophile carbon atom between nitrogen and oxygen atoms, which are extremely electronegative. Isocyanates can react with active hydrogen atom containing molecules such as alcohols, amines, water, and carboxylic acids. In addition, at temperatures higher than 100 Celsius, reactions between isocyanate and urea or urethane occur, leading to the formation of biurate and aliphenates. Diisocyanates undergo polyaddition reaction with polyamines to form polyurea. Here is the comparison between polyurea and polyurethane. Polyurea coatings are prominent with their rapid cure time and high film thickness due to their low volatile organic compound level comparing to polyurethane coatings. In addition, polyurea coatings can be applied at low temperatures and they have high UV stability and resistance to stretching. However, there are significant disadvantages of polyurea coatings. For instance, polyurea coatings have short pad life and high humidity sensitivity. Due to rapid reaction time, reaction kinetics limits high solid systems by decreasing mobility. Also, polyurea raw materials are more expensive. How about choosing the right amine? Primary amines react too rapidly with isocyanates, resulting in color instability. Aromatic amines require special equipment with sufficient raw material, mixing and dispensing features for the application, which can be costly. So, hindered aliphatic secondary amines are mainly used due to their relatively slow reaction times and easier applicability. Aspartics are secondary diamines with high steric hindrance. It undergoes polyaddition reaction with aliphatic polyisocyanates to form polyurea. By changing the X group in the structure, pad life and curing time balance can be altered for different applications. Also, the structure of isocyanates affects surface adhesion, VOC level, and application properties. Then, why polyaspartics? Polyaspartic ester-based polyurea top coats have longer pad life and they are non-yellowing. They have several application areas due to their relatively low viscosity and high reactivity. In addition, ability to form polyurethane-polyurea hybrids provides high chemical resistance and flexibility to obtain specific properties. Polyaspartic coatings have a wide range of applications, such as roof, floor traffic marking, and protective coatings due to their rapid curing time and water and corrosion resistance. Rapid curing time decreases the time required in furnaces and reduces energy costs, and it plays an important role in conducting projects with early deadlines. So our objective was gaining an insight into the polyaspartic paint chemistry. By investigating how pot life, dry time, and fill properties change with solvents, catalysts, resins, and hardeners. For this purpose, we did kinetic observations via rheology measurements and FTIR, also paint test and UV weathering. So let's begin with rheometry results. It can be seen that complex viscosity of polyurethane does not change significantly in 60 minutes, while complex viscosity of polyaspartic changed dramatically. This plot demonstrates the reaction rate difference between polyurethane and polyaspartic systems very clearly. You see storage modulus and time plot here. Storage modulus or elastic modulus indicates how much energy is needed to distort the material so that the slope for polyaspartic increases faster. Last factor shows the viscoelastic behavior. During the first hour of the experiment, polyurethane stays in the storage region, but polyaspartic quickly enters into elastic region. Also, FTIR analysis was conducted by observing the decrease of isocyanate peak intensity within 2 hours. As you can see, conversion rate of NCO is higher for polyaspartic. Let's look at paint test now. This data shows that polyaspartic material has lower VOC while having higher solid content and lower viscosity. Also, the polyaspartic that we prepared is in accordance with VOC regulations of European Union. Hardness test was not possible to conduct for polyurethane during the first day of application because it begins to reach the minimum required hardness for testing after 1 day. Polyaspartic hardens much more faster and is harder than polyurethane at the end of the measurement. As expected, dry to touch time is a lot shorter for polyaspartic in addition to dust-free time. Here is a pot life measurement. Polyaspartic material reaches its pot life within 20 minutes. On the other hand, during the time polyurethane is still viscous, its viscosity begins to increase after an hour, and the pot life of it is more than 6 hours. In this graph, temperature change with time of polyaspartic and polyurethane formulations are plotted. As shown in the graph, temperature does not change significantly for polyurethane due to its slow reaction mechanism. However, temperature increases with time for polyaspartic, which indicates that the reaction is exothermic. High temperature change indicates low pot life. Both polyaspartic and polyurethane give similar gloss values. Also, both of them give similar high R-spec and DOI values. Leveling property is higher for polyaspartic coatings. It can eliminate surface defects better due to its low molecular weight and flow properties. We also performed UV weathering. Delta E values are roughly similar for both coatings, which shows that their rate of color change is similar. As a result of this study, we concluded that with polyaspartic chemistry, rapid film forming is possible, and insufficient path life of the main concern with polyaspartics. VOC compliance can be achieved due to low viscosity of polyaspartic resins. Also, while polyaspartics surpass polyurethanes in many aspects, they are still a lot to improve and optimize. This study is very comprehensive and has a significant potential to conduct further. Firstly, same experiments can be repeated after increasing the solid content of the product to improve its path life. The moisture content on the polyaspartic systems, the effect of isocyanate types on the performance and properties of polyurethane polyaspartic hybrids can be investigated. Different formulations with different polyaspartic compositions can be prepared. The effect of solvents on reaction kinetics of the catalyzed reactions can be studied. Further experiments can be done to understand the reaction mechanism of catalyzed reactions between aspartic and isocyanate. Lastly, the effect of water moisture on curing can be studied. We are thankful for Ayça Biçen, Nazlı Güvenç for FTR analysis, Buğra Oğla for rheology measurements, and coatings were prepared, applied, tested by Ertan Demirkol, Faruk Güçlü, Ceyhun Köseoğlu, and Volkan Şahin. Thank you for listening. If you have any questions, feel free to contact me. I wish well for all of us during this challenging time due to COVID-19. Again, thank you.